In this video, we're going to talk about titrations. And we're going to answer the question, how can titrations be used to determine the concentration of an unknown acid or base in a solution? So titrations are used to determine the concentration of a reactant in an acid-base reaction. And we're going to look at something called pH. pH is a measure of how acid or acidic or basic a solution is. And it's based on the concentration of hydrogen ions in a solution. Our pH scale ranges from 0 to 14, typically, where if you're less than 7, you are an acidic solution, meaning you have a very high concentration of hydrogen ions. If your pH is equal to 7, you are a neutral solution, which is going to just be pure water. That's where your concentration of hydrogen and hydroxide ions are equal. And then when your pH is greater than 7, you are a basic or alkaline solution, meaning you have a high concentration of hydrogen ions. Okay, now when we do a titration, we're looking for what's called the equivalence point. This is the point where the acid and base have reacted in exact amounts, meaning you have an equal number of moles of hydrogen and hydroxide ions. Okay, so at the equivalence point, your pH is going to be equal to 7 because you are a neutral solution in most cases. All right, so this is a titration curve, and we are starting out with an acid. I know that we're starting out with an acid because our pH is about 1 when we start. So we start out with an unknown acid, and we start adding base to it. As we add base, notice our pH begins to climb. And then, after we've added about 25 milliliters of our base, you notice that the titration curve just basically goes vertical. And pH around 7 is where we reach our equivalence point, where the concentration of hydrogen and hydroxide ions is equal. As we continue to add base to our solution, to our unknown acid, there is now a greater concentration of hydroxide ions. Hydrogen ions. So our pH continues to climb, and we end up capping out around 12.5 on the pH scale, which again would be a basic solution. So on our titration curve, you're looking for the point where your curve goes vertical and where you reach a pH of around 7. That's your equivalence point when we're titrating a strong acid with a strong base. All right. Now, the endpoint is the point where the indicator changes colors, which will indicate that the titration is complete. So an indicator helps us identify when the titration is done. And your indicator should work where the endpoint and the equivalence point are going to be very close to each other. So indicators are used to signal the equivalence point. Phenolphthalein is an indicator that is used commonly in acid-base titrations. So it will help change color on the solution so we can tell when your titration is done. So when the pH is less than 8.2, it is colorless. When it is a pH of 8.2 to about 10, it starts to turn pink. And when it is greater than 10, it turns a deep pink or magenta color, meaning it's a basic solution. So when we are titrating up to about 7, our solution is clear. When it reaches about 10, it will be a dark magenta. We're looking for the point between these two, indicating that we are kind of in this range right here. Okay, so we're looking for that color change, and that will help us identify when our titration is finished. All right, so let's look at an example here. And I'll show you exactly how a titration works. So it says, what is the concentration of an unknown solution if 35 milliliters of 1.3 molar NaOH is needed to neutralize 15 milliliters of H2CO3? Okay, so this is going to be our acid because it's starting with hydrogen, and NaOH is going to be our base because it has hydroxide in the name. So if you notice, we have a lot of information in our question. We have milliliters and molarity for NaOH, and we have milliliters and only milliliters for our acid. So we always want to start with the quantity we know the most about, which is going to be our NaOH. So we have a milliliters and we have a molarity for our NaOH. And we are going to convert from NaOH to our acid, which is H2CO3. So we're going to start with our given. And if you recall, you can only start with milliliters. You should never start with molarity. So this is 35 milliliters of NaOH. And we're going to need to convert this into moles. We're trying to find the molarity of our H2CO3. So we are going to need to get moles. So let's convert this to liters. Then we'll convert it to moles. Then we'll do a mole ratio. And then we will find molarity. So there are 1,000 milliliters in 1 liter. And then, oops, I wrote 1 liter, 1 milliliter. 1,000 milliliters. Try to write it all in one step. Let's try that again. So 1,000 milliliters in 1 liter. And then the molarity is 1.3. So there are, in 1 liter, 1.3 moles of NaOH. Now we're going to do our mole ratio. So NaOH has a 2 in front of it. So for every 2 moles of NaOH, we have 1 mole of H2CO3. Okay, the last conversion factor is the trickiest when you're doing a titration. So if you recall, molarity is moles over liters. And if we cancel out units that we've written so far, we are left with moles of H2CO3. In order to find molarity, we want to do moles divided by liters. We currently have moles, and we want to divide by liters. We have 15 milliliters. That's equal to 0.015 liters. So I'm going to write that on the bottom, 0.015 liters. Now you're probably thinking to yourself, well, wait a second, these units aren't the same. Why are you doing? I'm going to put a 1 on the top. Okay, it's just kind of a placeholder. Now, when I multiply my units, so moles times 1 will give me moles on the top. And then I'm going to have liters on the bottom. Moles divided by liters is going to be the same as molarity. So I know I'm breaking a rule, kind of, for our stoichiometry, but this is how we're going to find our molarity. All right, so we're going to start by taking 35. We're going to divide 1,000. We're going to multiply by 1.3. We're going to divide by 2. And then we're going to divide by 0.015. And there's our answer. 1.5 molar is our answer here. All right, let's look at another example. It takes 7.3 milliliters of 1.25 molar HNO3 to neutralize 25 milliliters of barium hydroxide. What's the molarity of barium hydroxide? So again, we're looking at an acid and a base. We know 7.3 milliliters and 1.25 molar for HNO3. We only have the milliliters of barium hydroxide. We always start with the one that we know more about. So 7.3 milliliters of HNO3. Convert it to liters. Convert it to moles. Mole ratio. Find your molarity. So there are 1,000 milliliters in 1 liter. The molarity here is 1.25 molar. So that means in 1 liter, you have 1.25 moles of HNO3. Now we do our mole ratio. So for every 1 mole, scratch that, for every 2 moles of HNO3, we have 1 mole of BaOH2. And then our last step is going to be find molarity. So again, molarity is moles over liters. So we are currently in moles. We want to divide by liters. 0.25 milliliters. Start over. 25 milliliters is 0.025 liters. That's how many liters are in 1. So we put a 1 on the top here. So this last step is tricky because these units are not the same, and we put a 1 on the top. And the reason we're doing that is because our units are going to be moles divided by liters, which is the same as molarity. So let's plug this into our calculator. So we have 7.3. We're going to divide 1,000. We are going to multiply by 1.25, divide by 2, and then divide by 0.025. Okay, so there's our answer. And if we round this appropriately to 2 sig figs, we are going to get 0.018. That is going to be our answer. That's how you do a titration.